Welcome to another GraphGeeks talk. I'm Amy Hodler, and with us today is Russell Jurney, an applied AI consultant working at the intersection of large graphs and large language models. Today, Russ is here with us to talk about how to build large knowledge graphs using Spark GraphFrames. Welcome, Russ. Welcome everyone who's joining and joined. Russell has extensive background in both graphs and AI as a consultant at Graphlet AI, and has taken I would say, a lead role in getting GraphFrames updated for what people need to do today. So with that, thank you, Russell. Why don't you go ahead and take it away?
All right, thank you. Yeah, my talk today is large knowledge graph construction with Spark and GraphFrames. Obviously, Spark is a tool that's optimized for large data sets. When it comes to graphs, the number of nodes and particular edges tend to matter more than like the terabytes or gigabytes of data. I'll start out with a story. This is peak Russell, by the way. This was like a low weight at the beach. But yeah, so I got into networks because the Fairchildren, they work at Shockley Semiconductor. He invented the transistor, co-invented. He was like really difficult to work with, so they all left. And I saw this poster of the children of the Fairchildren, essentially, all of these descendant startups. And I was struggling as an entrepreneur in Atlanta, and I was like, this is how I think. This makes sense. I got to join one of these networks. And so I like analyzed the Atlanta security cluster and crowdsourced this map that was later in the newspaper. And it's, sort of like a node is a company and an edge is a founder that worked at one company and founded another. And that was just my first icebreaker network app. So GraphFrames has been around for a while. I think 2017, there was the paper that described it. It really described a new kind of graph processing that combined graph queries like you might find in the graph syntax of Cypher with data frame operations. And that's kind of what's unique about it. It's really a powerful and expressive interface that we'll see. But yeah, it's a package for a package. It's not a part of Spark. The goal at present is to get it into Spark. GraphX has been deprecated. And so essentially we're looking to replace it with GraphFrames. But first and foremost, we're trying to get the project healthy. There's 3 of us contributing on a daily basis to GraphFrames at the moment. And they're much more technical and competent at writing Scala, infrastructure code than me. And so I've done documentation mostly so far, but it's really exciting. We're fixing bugs. We just expanded the test capability, like using known good results for label propagation and other algorithms to give us more confidence that the answers are in fact right. And we're emailing all the time. And so the project has really made a comeback from not having a release. At this point, I think it's been 6 months. We're going to cut one by Easter, hopefully. But so we just added Spark Connect, actually, is the big thing we want to get out. Spark Connect is the newer way to interact with Spark. And like Databricks Connect uses it. The classic mode is eventually going to be deprecated, probably. And so that's an excellent feature that we're getting in. But yeah, the really exciting thing about GraphFrames for me is the pattern matching capability and its motif finding, stuff that we'll go over. But yeah, so it works for Scala, Java, and Python. So you can use it in all 3. A little bit of a note, I know most people tend to say nodes and edges, vertex and vertices. It's a synonym for nodes. There's a debate whether we should have an alias for nodes that points at vertices. I really want to add it, but there's the idea in a project that you should have one way to do something rather than ambiguity, so it's still under discussion. But I'll use vertex throughout to provide clarity. So running GraphFrames, there's now 2 ways to do it. The main way is when you run PySpark or Spark Submit or Scala, or the Spark shell, you run the -- packages option and specify the Spark. There's a website called Spark Packages. We haven't been pushing to Maven lately. We're getting the keys from the guys that used to do that so that we can resume pushing to Maven Central. But Spark Packages, it's on Databricks. I created an example actually in my GitHub where it shows how to use Spark Packages in your Maven build. But you just specify, at the moment, the latest version is 0.84, Spark 3.5, and Scala 2.12, you can see there. And it will run it with the jar included and the Python code when you boot Python and run it. There's actually a new development for 0.9.0. We actually packaged the jar with the GraphFrames package that we're going to be releasing. To date, there are a couple. There's a GraphFrames package on PyPy, and there's a GraphFrames-latest package. Neither of those are our officially supported package. It's actually going to be something new called GraphFrames-Py will be the package, and you'll just be able to install that and use, PySpark, and you won't have to do the packages argument if you don't want to. But once you do that, it's importable, and you can get going. So from GraphFrames, import GraphFrame, and a GraphFrame takes nodes or vertices and edges, two data frames. The vertex data frame has to have an ID field, everything lowercase. The edge data frames have to have a source, a destination, and a relationship. Thinking about adding a type to vertex, similar to relationship, but in practice you can put any field you want there and treat them as different types. One thing that is a limitation at present that I started thinking through how we might change and improve, there's a single schema for a graph frame, so you end up having to merge the fields. If you have a property graph, like I did this for, in the example, I used the Stack Exchange data dump, and there's votes and questions and answers and links, and so I essentially take all the fields and put every field from any record in all the records, so a lot of them are empty. This is how some data products work that are Spark based, like Sayari Intelligence does this. They have a single catch-all data type. It's not ideal, but you essentially have to reference. If you just show the record, there'll be like so many fields that it's a pain to see. You have to actually think about which fields you want to look at. That's the kind of the downside to this, but that's already done in the examples for you. You really need to, when you're building graphs in GraphFrames, to do sanity checks. When I was building I've done this a lot, and even still, when I was building the Stack Overflow, Stack Exchange for stats.meta, you can download any stats, any Stack Exchange site, actually, with the download tool that comes with the tutorials. But I made a mistake where a lot of my for one of the edges, like it wasn't a UUID, it was some text field that wasn't valid. So it's important to double check. So here I've got an edge count, and then I'm doing a valid edge count by joining the vertices with the source and dest of all the edges. And so the idea being that they better find at least one in there, or it's a disconnected graph, and I assert, like in this case, it should be connected, and so it's a sanity check. And I put asserts, that way you can just sort of die and address the problem. But yeah, you really have to be careful when you're working with data frames and data flow, as opposed to a graph database where you've already decided on the structure, you put it in there, and it enforces it. This really comes before that stage. The outcome of building a graph in GraphFrames is something that you could put in a graph database, or you could use it for graph machine learning. Yeah.
Russell, since you brought up other graph solutions, I thought maybe this would be a good moment to ask you to give your opinion on why Spark and why GraphFrames versus other solutions that are out there.
Yeah, graph databases are mostly good at running pointwise operations. There have lately been some changes to this, but for a lot of interesting work with graphs, you really need to modify the entire graph. You need to apply an algorithm to the entire thing and transform it. And that is something that Spark excels at. And so there's also, once you put your data in a database management system as opposed to just a data frame like you probably work with in Pandas, there's a lot of overhead just to work with it. And finally, I think the data frame sort of hybrid graph mode is very expressive. And when you're figuring out how things relate to one another and you're building those relationships. It's just very kind of clean and free. It sort of feels right. But, if you need to do sort of in your application, so the idea with GraphFrames, and this is a common thing with a lot of graph analytics or graph machine learning, to the greatest extent possible, you try to pre-compute the answer and then serve it in a simple app. Like at a company I started called Deep Discovery, we built a 3 billion node, 2.2 billion edge, a knowledge graph by combining a bunch of business registry data sets.
Russell, the other thing that occurs to me is that if your data is already in Spark, you don't have to move it out.
Yeah, so when your data is big, it's on Spark so that you can efficiently process it. And so you really don't have the option of doing this kind of work in Pandas or NetworkX. So that's generally when you want to use Spark and GraphFrames. I use it for smaller projects because I've gotten good at it and enjoy the interface. But generally, you're talking about, what is big data? It's data that's uncomfortable in a database. And so, I always hear like really widely varying numbers on what's the largest deployment of any given database. But when you're pushing certainly a billion edges, most of the databases, the graph databases, struggle. And so that's something to keep in mind. But it's also like if you have a data lake and you have this compute capacity, even if the data that you're building into a graph is not large, a lot of companies have Databricks, or they have workflows in GCP Dataproc or Amazon Elastic MapReduce, and you can build a graph out of data and transform it into a form that will allow you to do machine learning, or load it into a graph database once it's refined. And so this GraphFrames is really good at, and Spark are really good at knowledge graph construction, that kind of upfront phase where you're transforming different data sets. They could be structured, semi-structured. You could be doing, relation extraction, named entity recognition, and, adding that stuff to the graph as well. The other library I'm going to talk about today is this really cool one that I've discovered lately, Mercury Graph. It has, node2vec, a common embedding that will work and scale up to large networks. It's got a Louvain modularity and spectral clustering. It also has like a random walk component that I'm going to implement struct2vec. It's a structural embedding, so you can use it for role discovery as opposed to just clustering. It'd be really nice to have both. So Mercury Graph is super cool. Yeah, so when I talk about building a 3 billion node knowledge graph, data set order is really, really critical. There's a lot of overhead when you onboard like a large data set. If you license, a large data set, just figuring out what it contains and profiling it can take time. There's often an evaluation period, but it's usually not adequate. And so you sort of almost, when you buy a large data set, don't exactly know what you're buying. When you pull the trigger, you have some idea from initial profiling, but that was the case for us with Sayari, which is an amazing data set. We didn't really understand what we were getting initially. If you can get away with a single large, source of data, and sort of ship your project or product, as opposed to doing entity resolution across multiple large data sets, that is definitely a strategy that you should employ. But it's essentially what can get you to critical mass for your specific use case. There's an attitude in some projects and some companies where it's like, we're going to get all the data, like as much as possible, and then we're going to jam it together. And it's exciting. It's totally exciting. But there's overhead with scale and complexity, and so it's really important to base things around use cases and get the minimum amount of data that you actually require to satisfy a use case, a specific use case. So you might be importing data from a relational database. You can compose a property graph through denormalization. The join keys essentially are your edges. They're sort of already provided. Semi-structured data can get fairly complicated in emitting edges from these, but in Python you can kind of yield or emit edges directly from them in Spark. A lot of times there are existing network data sets you can use that you might not have to transform a great deal. And then in text, I would definitely recommend if I did a survey recently of the latest tools, and I found that, and this is something that Paco has worked with, I found that the stack of Gliner and Glyrel, Gliner for NER and Glyrel for relation extraction, was the best stack available in terms of tools with custom transformers for information extraction. But I really did feel that I would probably get better results with something like Pydantic AI and just fine tuning like a prompt to get me the structure that I needed. That was for technology sort of articles and coverage and startup home pages, so it might not apply to everything. But there was a library called New Extract, which is very interesting. It will extract any JSON structure that you give it. There was another called, I forget, but I'll get that post out at some point. And so essentially what you need to prepare is a node edge list of type semi-structured records. So the nice thing about data frames is you can have sort of arbitrarily complex fields in your graph data. And so this facilitates, for example, if you performed entity resolution and you merge fields, a lot of fields can become lists at that point if it's like a compound node. And so it's nice to have a data model that supports that type of thing. There's a really wide variety of processes to build a graph from, structured or semi-structured data. We dealt with data at Deep Discovery that was like often handwritten into a form and then scanned. And so it was really quite dirty. Other times people might have data from logs or generated by machines that is much cleaner and more direct. There might be a bunch of types already defined, like for security events and log types and things. Other times you're dealing with data that has been information extracted from documents, and sometimes you don't have visibility into that process, and it can create a little bit of impedance with what you're trying to do when you don't quite understand the source origin of the data you're putting into your graph. But so generally I create a unique surrogate key like a UUID, although there are some alternatives that ULID, I think it is, that are a little bit more efficient. But I generate one for each record, and then edges, have two at the source and destination UUID. That just is the simplest way to get everything, a non-sequential ID. I find it works well. So, what entity resolution do you need? Without entity resolution, we're going to talk about like motif matching. It essentially, in my experience, doesn't work unless depending on the data, obviously, but in doing, your customer checks and anti-money laundering stuff for entity resolution was applied to the data. I essentially detected no patterns that might be indicative of crime. And, so it's a really important topic. I'm going to go over some architectures that can be employed to handle it. But
So Russell, as you're going on to entity resolution and motif finding, you made the comment that you have to have entity resolution in order to find motifs, and motifs equal patterns, but there's a nuance there that not everybody might be familiar with. Can you explain the difference between just finding a pattern and motifs and motif finding?
Yeah. So this kind of talks about it, this slide. Entity resolution kind of facilitates pattern matching. Like on the left are 3 nodes that represent one person. And I can actually show you open corporate stock officers, Russell Jurney, all jurisdictions. There's like quite a lot of forms of my name. It used to be a Rush Jurney, but it fell off. But there's this many of me and unique instances, and they're really cool that the way they handle their data openly. But so if you wanted to understand kind of me as an entity for the purpose of verifying my risk to a bank in terms of money laundering or funding terrorism, entity resolution is really important. And so you can see here, there might be 3 entities of me. Only one has a link to this other person that might be risky. Maybe they're a terrorist. But when you apply entity resolution and apply edges between person A, you get that kind of overall, this is friend and not terrorist, but you get that overall friend edge, and that greatly improves the quality of the data for pattern matching. And so if you had, a property and person entity A1 that you're looking for, that's why prop 1 is in bold, in a search, and then you want to find out like who they're connected to, you simply couldn't do it without entity resolution. And there are a lot of problems that are, depending on your domain, related to entity resolution. Like we had to do subsidiary matching, and that's not, it's almost entity resolution. The addresses could be in a different state. We would look at like the name would be similar, but it might have a different ending, especially if they were international, but the officers would often be the same, like from a pool of 4 or 5 people for a significant corporation where they would appear, I don't know if it was like the lead counsel or something, but there's and then you from there you kind of merge into the motif space. So it's almost like a continuous spectrum from pattern matching and entity resolution. There's a tutorial that I created that I'll put in the GraphGeeks channel. I think I might have already done so, but it takes you through and in the Stack Exchange data, and I'll show you a little bit of this in a notebook today, but it takes you through and really profiles that data and tries to understand it by using just some of the standard patterns that you see there, and then kind of leaving the edge type and node type free to vary and just counting them and see what comes up. It's a really nice way to profile data. These are undirected graphlets. So a graphlet is a standard structure in a graph, and these are the 30 up to, graphlets for up to 5 nodes. When you go past 5 nodes, the potential combinations go up really quickly. I think these are the directed graphlets. So there are more, 48, it looks like 48 or 49. And so a graphlet has different, I think they're called orbits, and those are the unique positions within the pattern. When I talk about motifs, a motif technically is a statistically significant graphlet. So if you're doing this rigorously, you're supposed to have a random graph model of your network that you fit to it. So if it's like a long, a power network where you have, or a small world network, most networks, don't match like a random, like a Erdős-Rényi, a sort of randomly selected connection type of network, but you essentially look for patterns that are too common or not common enough that you would expect to be there. And it's not necessarily the case that statistical significance is business significance, but it often can be. And so that's kind of what the technique is. Here's sort of covers what I was just talking about. Yeah, so network motifs came from biology in 2002. You play around with them in NetworkX. This was sort of some of the first network motifs that were mapped. You have like a feed forward motif is common in biology, where kind of A will stimulate B, which both stimulate C to kind of get a biological process up and going. It's like a feed forward motif. Here you've got, a triangle, and on the right, I was talking about random networks, like, you can see on the left, the real network has a bunch of triangles of this certain structure, and the random networks on the right have very few. And this is why it's sort of often said that, network motifs, these patterns are the kind of the building blocks of really rich, vibrant networks, complex networks that encode a lot of meaning that you're there to figure out and model and abstract. And so there are heterogeneous graphlets for, because we don't use mathematical models when we compute, we use databases, DataFrames. And so this is sort of a closer model than what we saw before. The combinatorial complexity gets a lot more difficult when you have both node and edge types that vary. Although there's a paper that asserts that you can essentially do a heterogeneous network motif match for the same price as a standard one, and I can't quite, or at least the same scale of complexity, I can't quite wrap my head around that one. So I looked for a long time for a null model to model a property graph, and I've got a candidate, but essentially what we ended up doing at Deep Discovery, we took some domain knowledge and we looked for what should be there, and then we created variations and we looked for those, and we kind of looked at the results and used it as an investigation tool. So pattern matching was something that we could do on top of normal kind of investigative querying. So you can see like the total number of type motif orbits with 4 nodes that arise from 7 types is 10 times 210, 2100, since there are 10 connected 4-node homogeneous motif orbits. That's hard to wrap my mouth around, let alone mind. And so basically the problem with network motifs is that they've traditionally been very difficult to compute. And this is why GraphFrames is very cool. And what it does, it takes a big data approach and, just sort of throws compute at it and does joins to implement the motif matching. And that's kind of its model. This is a property graph model, property graph motif. They didn't name these things in the paper. They talk about motif matching in a property graph. And I emailed them like a few weeks ago. I'm like, why didn't you call them property graph motifs? Because it's like a new kind of thing, especially where you can apply aggregation. The API will return a path. So here's an example of a business graph motif for financial secrecy. It's called multiple path indirect ownership. This comes from Bureau van Dijk, where they have a number of patterns for hiding ultimate beneficial ownership. And so Company A wishes to hide the fact that it owns Company C, and that could be a person as well, just an entity. And so they have a majority ownership in a series of companies in the middle, companies B1 through BN. And in combination, those companies own a majority controlling interest of Company C. So Company A is in fact in control of Company C, but is the ultimate beneficial owner. They would decide where any revenue goes, and so they're essentially hiding their ownership, which is, sometimes there are valid reasons for secrecy, but if you're, like a politician's relative and you engage in this kind of behavior, these risk factors like start to add up and they drive investigations, and that's how money laundering is fought, and crime and corruption and that sort of thing. This is the code for that motif. So what you actually have to do here is you have this, it returns a path, a set of paths. So you get essentially A, B, and C, and the edges between them. And so you have to group the Company A and Company C, and then count the majority ownership. You have to sum all of the ownership percentages in the middle to see if it's enough to control Company C. And so that's why I call them property graph motifs, because you're actually also applying relational operators, and you're getting something that's kind of a hybrid. Sometimes, depending on the data, these are kind of things that you might arrive at by SQL queries or just general analytics, but it is a different way of arriving at them, and it has a lot of potential. So you can see here, like the A dot type equals company. It has to have more than one connection, so its degree is greater than 1, or it can't connect to, it wouldn't constitute the pattern if it were just one middle node. The AB is the edge. So you can see here these patterns. A connects to through edge AB to B. B connects through edge BC to C, and so that's essentially it's like a cipher graph query syntax. They only go to the right at the moment. That's changing. One of the new committers, Sem and Angel, are the GraphFrames heavy hitters. They're working on changing that so that you can also have bidirectional edges or move to the left. But you essentially then can apply pretty complicated logic to just by filtering, and suddenly you're not in like this is a mathematical model that doesn't really look like your data or your job. Okay, but this is something that you can really do real work with. And so That's why I got really excited about them when I first discovered them. I didn't even know what a motif was, but I had done pattern matching in the past when I was working on sales and marketing networks, partnerships and example customers. And, I just sort of figured this stuff out while I was working on deep discovery. But you can see, as I mentioned, I group by A dot identifier and C dot identifier, and then the second edge percentage, and call it total ownership percentage. What you have to do at that point is label the original nodes with the orbit that they're in. So you essentially end up adding the motifs on top of the graph as labels. So, node A would get like an ultimate beneficial owner label you would say it's this kind of pattern. It is company A, orbit 1 in multiple path indirect ownership, because if they're participating in that, they're engaging in financial secrecy, and they're more risky to a bank. And so, and then you would label the company B companies as having that position. They're essentially shell corporations, and the actual asset that is owned, you would label that as well. And we actually ended up doing this. We couldn't easily find a graph database that met our needs. I think it's probably easier today, but we ended up using like OpenSearch as a graph database. I've done this a couple times because my query requirements were low. They weren't complex. So we could do a couple of hops with like an OpenSearch plugin, and it saved a lot of money on a graph database. But if you do have to do live querying, it's a little bit different.
Russell, quick question here. I got a quick question, and one is about just having tried to do motif finding several years ago in a graph database where you have a very simple motif, and so the number of matches was so exponentially high that we just couldn't do that on a large graph. But if I'm looking at your filter items within that, whatever that last screenshot, or here, do you filter ahead of time as opposed to filter afterwards, and therefore you're able to compute at a larger scale in DataFrames? Or why is it you can do that like that? I'm just looking at the GDOT find, like I wouldn't be able to do that simple type of motif in a really, really large graph, but you can on GraphFrames. And just why
it's because it's like a full-blown SQL engine, and they push filters down, I think is the term, so that it does reduce the IO. Like when it reads, it filters essentially. And so, I remember with Hadoop, filter push down was a major thing. It would reduce the amount of data that flowed. So I think that is what is going on. I don't have a full understanding of that, but I think it reduces the number of paths significantly. So here's another. This was kind of the most complicated motif we put together. It's like someone bought an incorporation services company and they corrupted it, and so they had, this person was person A. They had a bunch of companies that were managed by actually the same 5 or 6 people. And their names varied the way that mine does on open corporates. And so we actually used embeddings, to get like a semantic match for the name so that it would work approximately so that Russ would match with Russell. And what you can actually do once you get motifs, it's just like in entity resolution, like Senzing always represents things as a list, like a list of addresses, a list of, you can essentially, this is trying to show rolling up property graphlet minors. Like a graph minor is a transformation of a graph I don't know if I can define a graph minor, but it's like if you had a triangle motif, it could become one node, essentially. So then you can combine all the edges, and suddenly patterns that were nearby kind of merge, and you have like these locus of risk. And so motif clustering is a technique that you can employ. So I've got some actual pay dirt. I put together a notebook, and I already ran it. I'm not going to try to run it because some of the stuff does take a minute on my machine. It's much faster on my Linux machine. This is my Mac, and you basically, from Graph, let me bump the size significantly. That's probably a lot better. There's this library, Find Spark, that I needed because it's a Jupyter notebook. Normally, you don't really require that. But so set up the Spark session, all the normal Spark setup stuff. To run some algorithms, you do have to set a checkpoint directory. And then I have already prepared these nodes and edges for the stats.meta.stackexchange site. So there's like 129,000 nodes and 97,000 edges. I count them by type. There are badges, votes, users, answers, questions, post links, and tags. This is the subject of this network motif tutorial, which I will type to you once I'm able. But there are these relationships, earns, I think that's like badge, cast for, vote. Tags is something a tag does to a post. And this was, it's not like a super sexy data set, but it's like simple enough that was able to detect kind of interesting patterns. And so, so here's some features of GraphFrames, since that's kind of what we're here to talk about. There's PageRank works well. There's connected components is really useful for entity resolution. If you add edges between records that need to be linked and merged, you can then get a connected component, and that'll give you a unique ID for each group that needs to be merged. And so this is probably the most used feature of GraphFrames. People use it for their big data entity resolution, and it's a little bit, I think, like SSL in that regard, where it's kind of at the root of some things, but not always appreciated. So you can look at the connected components of what size. So there's like a large component. This is pretty common. Strongly connected components as well. They're obviously smaller because every node has to be connected to every other node, but it's 19. So 19 nodes are fully connected with every other node, which is really interesting, actually. I'm very curious what that would be. And so this stuff is often a jumping off point. So I wanted to demonstrate network motif finding. These are actually just nodes and edge records, but when you do a find, it returns them in a, like all at once in each column. So they have this form where it's just showing this is the unique ID for the node, or this is the source. But you can expand them if you change a setting. But ultimately, you do need to like kind of pick out what you want to show. So I just did A to B, A to C, C to D. So then I want to examine it. So I take the type of each node, and I take the relationship type, and I go ahead and label it as A, E1, B, since that was what it was in the pattern, just to help myself out. And you've got the B type and C type. And then I'm going to group by all those values and get a count, an order by the count descending, so that I'm essentially profiling the data set in terms of the different patterns that are in it. So you can see it's like, a tag tags a question, which is, it tags another question, and that question links to another question. You have to it's a little bit tricky to read them. It takes a little practice. Because if it's like a straight path, it's easier, but it's a lot of fun actually when you get to do it. So here's some interpretation. There was a tags question B, tags question C links to question B. So a tag is used on a question, that tag is used on another question, and the two questions are linked. So that's a pattern that emerged. So
Russell, I don't think people. I'm going to pause for a second and just say that is really complicated to do in a lot of systems. So just watching how simply you've put that together, and then you can do all sorts of things with these little motifs that you've found. You can link them together. You can consolidate them into, a grouping and do all sorts of fun things. But that, this, A to E1 to B, and then E2 to C, that computationally, that can be very expensive in a lot of systems. So it may look simple, but this is not easy stuff to do. And Russell, we have about 8 minutes left. I'm going to start to open up mic so people can just like jump in with questions. But one thing I'm assuming that people are wondering in their head is we've said there's a lot going on with GraphFrames. There's a lot of changes. There's going to be a major commit in the next month. Are there some caveats or some tools or resources people should be, looking at or following, especially as these changes this spring are coming up?
There's a 0.9 release. If you go to the GitHub, we're going to be organizing things under the 0.9 release. We're trying to ship it by Easter, basically. And so things will get a lot better at that time. The current release is about 6 months old. It works reasonably well, but we've added a number of features and fixed a number of issues. And so, yeah, Easter will be the time to pick up the new and improved version. We do have the GraphFrames channel on GraphGeeks where some of us hang out and discuss GraphFrames. So if you're interested in getting help.
Hello?
Ramona. Yes,
Oh,
Ramona,
hi.
go ahead.
Hi. Thank you very much, Russell and Amy, for organizing this. So what I want to get at the end, and I've actually already asked this, I'm trying to understand what is the biggest use case for this? Because yes, we can do a lot of things. I appreciate Spark and and what it can do, but if we are looking for a particular, to whom would you recommend this particular solution as opposed to others that exist there?
Yeah, so this was really powerful for us. We were pursuing a graph neural network architecture to do classification of risk in the network. So we had a machine learning solution. It turned out what they wanted were just the patterns that denote risk. Banks are really good at determining what risk is. They just wanted us to tell them, in an indie resolved knowledge graph, what the risk factors were, and that would have been sufficient to sell the product. So this is like another take on how to work with graphs, essentially, that you can add pattern matching to the mix, and maybe it fits the problem that you're working on, especially if you're struggling with graph machine learning. Like biology is the area where these are used the most, like proteins and genes interacting. They're used in financial transaction analysis is a big one. I've had a sort of pet project trying to bring that over into business graphs as well. But those are the two that I'm most familiar with.
So I guess I will a little follow up, and Amy already asked this question. Why using this when we can do the same in Neo4j, for instance? Like, what is the main selling point there? And I know that fraud detection is a big use case for Neo4j, and also I'm assuming in biology and proteomics and all of that. So there are well-established solutions. So I'm just probing a bit more. I hope you don't mind, Russell.
No, I don't mind at all. Like I said, big data is usually what doesn't fit in a database easily. And so if you're dealing with billions of nodes and edges, a Neo4j might not be the best graph database for you as compared to something like Spark that scales better than that. Also, if you're applying algorithms to the network that process all of the nodes, that's a time when you might not get the performance that is required.
I'm just going to jump in as well and just say there's also if your data is already in Spark and you're already a Spark user, bringing graphic capabilities to where your data already lives is really attractive to a lot of data managers, because you don't want to, as soon as you make a copy of your data, then you have to worry about changes to the data. You also have to worry about storage for the data. And so anytime you can, especially if you need just some graph analytics over the data you already have, if you can bring it where that data is something is a big selling point for a lot of businesses. So.
Yes, because you don't need the transformation layer in between, right? So that's, yeah, exactly.
Like if you have a well-formed graph, go ahead and put it in Neo4j, but this is knowledge graph construction. It's the phase before that, where you don't necessarily have something that fits into a clean schema in a graph database so that you can run the queries you need to run, where you need to refine that graph, clean it up, do things like information extraction or entity resolution. And, if your data is already on Spark, it can be a pretty effective way to work.
And there are connectors between Spark and Neo4j as well. So people do go that direction. So unfortunately, with that, we will just time-wise have to leave it there for today. But thank you everyone for joining. Thank you for the good questions during, and follow up with Russell or on Discord for more information. Thank you, Russell. Always so much good information, and I know you've done a lot of work that you didn't get to cover. So let's have you on again, and definitely find Russell online and ask some questions if you had. So thank you, everybody.